Welcome back to QHSE Talks.
Glad to be here, as always.
So imagine you are standing under a 10,000-pound load, right? It's suspended 40 feet in the air.
That is a terrifying place to be.
Right. And knowing the only thing keeping it from literally crushing you is a mathematical equation. Like an equation dictating exactly where a counterweight sits on the back of the crane.
Yep. If the operator miscalculated by even a few feet, well, the entire system collapses.
Exactly. And that is the reality of occupational safety. I mean, it isn't just paperwork and, high-vis vests. It's applied physics. It's behavioral psychology. Yeah. And it's rigorous systems management standing between a worker and a totally catastrophic failure.
And that reality is exactly why we are here today. The stakes are incredibly high for you, the listener, and the workers you protect, which is why the framework for managing those stakes it has to be ironclad.
Which makes this a massive milestone. I mean, this is the final session of our ASP 11 Domain 2 playlist.
It really is a huge moment.
Yeah. And if you've been following along with us, you know we have covered a staggering amount of ground together. So I just want to say thank you so much for sticking with the show through this whole playlist and learning with QHSE Talks. You've put in the work, you've learned everything in Domain 2, and today we are going to bring it all home.
That's right. We are doing a comprehensive review and revision masterclass, and we are focusing strictly on Domain 2 topics today.
The mission today is to consolidate all of that knowledge, right? We're overviewing every single topic we've covered to ensure you are fully primed and confident for your ASP or CSP exam.
Absolutely. And to do that, we are pulling from a really heavy stack of authoritative texts. We've got the CCPS guidelines for risk-based process safety, the ISO 40501 implementation guides, the ANSI Z10 standards, and actual CSP exam practice problems from Bowen EHS.
So think of me as your ultimate study buddy today, keeping the energy up. And think of our expert here as your personal instructor, giving you that critical final review before the big day.
I am ready. Let's get into it.
Awesome. So we are skipping the superficial definitions today. We're looking at the actual mechanics of these concepts. Let's look at where every solid safety program actually starts, which is topic 1, right? Safety management systems, specifically ISO 4501 and ANSI Z10.
The foundation of it all.
Yeah. And from my reading, both of these frameworks, they're built on the classic continuous improvement cycle, right? The plan, do, check, act cycle. But they seem to approach the human element with a really specific philosophy.
They absolutely do.
Yeah.
ANSI Z10 doesn't bury the human element in the middle of the document somewhere. Yeah. It places it at the very beginning. Section 3.0 is management leadership and employee participation.
Okay, so it's front and center.
Right. The standard dictates that without those two forces working simultaneously, the rest of the system is just, it's a theoretical fantasy.
Let me try a mechanical analogy here to see if I've got this. If we think about the safety management system as a car, management leadership is the engine, right? It provides the capital, the resources, the momentum. But employee participation, that's the steering wheel.
I like that.
Because if you have an engine but no steering, you're just going to crash into a wall. But why does the standard insist that both are required right out of the gate? Like, why is it step 1?
Because, honestly, a policy drafted in a boardroom almost never survives contact with the factory floor without worker input. Management provides the accountability, sure, but the employees are the ones actually facing the operational realities every day.
Right, they see the actual hazards.
Exactly. They are the ones who can look at a proposed safety control and tell you if it actually fits the workflow or, if it introduces a new unseen hazard. Safety isn't something management does to employees, it's something they do with them.
That makes total sense, especially when you look at the recent revisions to Z10. The 2019 revisions specifically aligned its high-level structure with ISO 4501.
Yep, the Annex SL structure.
Yeah, and I assume that was to stop companies from having to build two completely conflicting systems if they wanted to meet both American and international standards.
That was the primary driver, yeah. ISO 4501 is a global standard. And by aligning Z10 with it, organizations can integrate both seamlessly. They operate on the exact same fundamental logic now. And there is a critical exam tip tied to this exact philosophy, run straight from our Bowen EHS practice questions.
Oh, lay it on us.
You might see a question asking whether safety management is primarily an educational, enforcement, engineering, or motivational problem.
Oh, I remember struggling with that one initially. My gut immediately said engineering because, we spend so much time on guarding and physics and math.
Most people guess engineering. But the answer is that safety management is primarily a motivational problem.
A motivational problem. Interesting.
It is a systemic motivational issue. Think about it. You can engineer the safest, most redundant machine on the planet. But if the culture is toxic, if management silently encourages bypassing guards to meet production quotas, and employees just aren't motivated to speak up, that machine will eventually claim a limb. The engineering is secondary to the motivation.
Wow. Okay. So once we have that motivation and that management system locked in, Z10 dictates we move to Section 5.0, implementation. We have to actually control the hazards, which brings us to topic 2, the hierarchy of controls.
The blueprint for safety.
Exactly. But let's not just list them out. Let's look at this like fighting a disease.
Oh, I like where you're going with this.
Yeah.
Let's walk down the hierarchy using that lens.
Okay, so at the very top, we have elimination and substitution. In my mind, this is the vaccine. You're entirely eradicating the threat so it never even reaches the human body.
Right.
And the texts give a great example of substitution, swapping out a welding rod that contains hexavalent chromium for one that contains copper.
Or moving a hot work brazing operation out of a combustible dust environment entirely. You haven't just shielded the worker in that case. You've designed the explosive potential completely out of the equation.
Which is the dream, right?
It is the most robust defense. But, as you know, you can't always eliminate the hazard. Some processes inherently require dangerous chemicals or massive kinetic energy.
Right. So if we can't use the vaccine, we move to the next best thing, which is engineering controls. This feels like quarantine to me. We are physically isolating the hazard away from the vulnerable population.
The key word there is physically. We are altering the environment or the equipment, not the human behavior.
Give me a real-world example of that.
Okay, if workers need to inspect skylights on a roof, building permanent stairs instead of relying on extension ladders is an engineering control. Or take acoustic hazards. If you have a 100,000-pound drop forge generating like 120 decibels, the engineering solution isn't to hand out better earplugs.
Right, because that's PPE.
Exactly. The engineering control is to build an acoustic enclosure around the forge itself, absorbing the sound energy before it even propagates through the air.
But engineering controls can fail, or they might be economically unfeasible for a small operation, right? So we step down again to administrative controls. If elimination is the vaccine and engineering is quarantine, administrative controls are like mandating hand washing.
That's a great way to look at it.
We are trying to change human behavior through policies, training, and procedures like lockout, tagout.
And that reliance on human behavior is exactly why administrative controls sit lower on the hierarchy. Humans get tired, they get distracted, they take shortcuts.
Yeah, we're fallible.
Right. A physical barrier doesn't forget to do its job, but a worker might forget to sign a hot work permit. Administrative controls aim to prevent exposure, but their failure rate is directly tied to human fallibility.
Which drops us to the absolute bottom of the barrel, personal protective equipment, or PPE. This is taking medicine after you've already been exposed to the disease. The Bowen EHS questions push really hard on why PPE is the last resort. And it's not just because it's annoying to wear, is it?
No, not at all. The physical mechanics of PPE explain why it's the last line of defense. First, PPE does not eliminate or reduce the hazard in the environment. It merely creates a highly fragile barrier between the worker's body and the hazard.
It's just a thin line.
Exactly. If a chemical splash hits an engineering control, like a splash guard on a machine, nothing happens to the worker. But if it hits a worker's protective suit, and there is even a microscopic tear in the fabric, the exposure is immediate and devastating.
And PPE can actually create entirely new hazards too, right?
Constantly. Heavy chemical suits induce severe heat stress. Respirators increase the cardiopulmonary load on the worker. Safety glasses can fog up and restrict peripheral vision, which leads to struck by accidents.
Oh man, that's a good point.
When you take the exam, always look for the scenario that asks you to select the most effective control. The test makers will give you 4 technically valid options, but you must select the one highest on the hierarchy.
Always go for elimination if it's there. Okay, so we understand how to mitigate hazards once we find them, but how do we hunt them down methodically in the first place? Let's move to topic 3. We have an entire alphabet soup of hazard and risk analysis methods to review.
We certainly do.
We've got HAZOP, FMEA, what if, fault tree analysis, Fishbone, change analysis. It is really easy to get these jumbled. Let's break down the mechanics of each one.
We should frame this using the CCPS guidelines for risk-based process safety. They ask 3 fundamental questions. What can go wrong? How bad could it be? And how often might it happen?
Okay, that simplifies it.
Every analysis method is just a different lens for answering those three questions. Let's start with HAZOP, the Hazard Numberability Study.
HAZOP always seemed incredibly rigid to me. It's not just sitting in a conference room brainstorming, is it?
Not at all. The core mechanism of a HAZOP revolves around the concept of deviations from design intent. You break a massive system, say a chemical refinery, into tiny manageable nodes, like a single section of pipe.
Just one pipe.
Right. Then you apply specific parameters to that node: flow, temperature, pressure.
So you look at the pipe and ask, what happens if we have more flow, less flow, reverse flow?
Exactly. You systematically force deviations using guide words. It is highly structured and parameter-driven. It forces the engineering team to consider states of operation they never actually intended to happen.
Okay, then we have FMEA, failure modes, and effects analysis. How does that differ from a ZY? Because FMEA seems to focus less on the flow of a process and more on the physical parts themselves.
FMEA is a bottom-up approach focused heavily on component failure. You look at a specific widget, a pressure relief valve, a relay switch, a bearing. You define its failure mode. Let's say the valve gets stuck closed.
Okay.
Then you analyze the effect of that specific failure on the immediate subsystem and finally on the entire plant. You are building from the bottom up.
So if FMEA is working from the bottom up, building the system piece by piece to see what breaks, fault tree analysis, or FTA is the exact opposite, right?
FTA is top-down deductive reasoning, yes.
I've always thought of FTA as a detective working a crime scene, whereas FMEA is a building inspector.
Oh, explain that.
Well, the building inspector, that's FMEA, they test every single brick and pipe before the house is built to see what might happen if one cracks. But the detective FTA arrives after the house has already burned down. The disaster is at the top of the tree, and you have to deduce your way downward to find out what caused it.
That is a brilliant heuristic for the exam. The detective versus the inspector. And to push the FTA detective analogy even further, they use Boolean logic gates to solve the crime.
Oh, like and/or gates.
Yes. An ANDI gate means two specific failures had to happen simultaneously to cause the next event up the tree. An OR gate means either one failure or another could have caused it. This allows you to calculate the exact mathematical probability of the top event occurring.
That's super powerful for complex systems, but for less complex operations, we have the what-if/checklist method.
Which is exactly what it sounds like. It combines the creative, informal brainstorming of asking, what if the power goes out during this batch run, with the structured rigor of cross-referencing those scenarios against a predetermined checklist of known historical hazards.
Oh, perfect. Now moving to topic 4. Once we've used these methods to identify all these potential disasters, we have to quantify them. That is the risk matrix methodology. It calculates risk as a simple product, right? Likelihood multiplied by consequence.
Or, in industrial hygiene terminology, exposure rating multiplied by hazard class. You plot probability on the y-axis and severity on the x-axis. But, the true value of the risk matrix isn't actually the math.
No. What is it?
It is its function as a translation device.
A translation device for management, you mean?
Yes, exactly. Engineers speak in technical probabilities and failure rates. The C-suite speaks in resource allocation and budget. The risk matrix translates complex engineering vulnerabilities into a color-coded grid.
Ah, red, yellow, green.
Right. When a safety professional can point to a bright red box in the upper right corner and say, this is a high-probability catastrophic severity risk, leadership instantly understands why capital needs to be deployed immediately.
That communication aspect is huge. And speaking of communicating hazards, let's pivot to topic 5. Chemical management and the globally harmonized system, or GHS. Because if we can't eliminate a toxic chemical, we have to make sure every single person handling it understands the risk, regardless of what language they speak.
And that was the United Nations goal in developing GHS, a standardized universal system for classifying and labeling physical, health, and environmental hazards.
The labeling requirements are super strict, right?
Very. You need the product identifier, supplier info, and the standardized pictograms. But you also need hazard statements and precautionary statements.
Let's clarify the difference there because they sound really similar, but they serve entirely different functions. A hazard statement is just a factual declaration of the chemistry's effect on biology or the environment. Something like causes severe eye damage.
Yes. It describes the nature of the hazard. The precautionary statement describes the response. Wear a protective face shield. Or, in case of contact, flush eyes with water for 15 minutes.
All right, that makes sense.
Furthermore, you must understand the two signal words used in GHS. They're not interchangeable.
It's danger and warning, right?
Yes, and the distinction is critical for the exam. Danger is reserved exclusively for the more severe hazard categories. Warning is utilized for the less severe categories. If you see a label with danger, you are dealing with a chemical that has a significantly lower threshold for causing catastrophic harm.
To make this concrete, let's tie chemical hazards back to the industrial hygiene sampling practice questions from the sources. There is a specific scenario regarding ethylene oxide.
Oh, that's a classic one.
Yeah, so the setup is ethylene oxide has a short-term exposure limit, or STEL, of 5 parts per million. The permissible exposure limit, the PEL, is 1 ppm. The question asks how you appropriately sample to ensure employees aren't exceeding that STEL.
This tests your understanding of time in relation to hazard exposure. A PEL is based on an 8-hour time-weighted average, or TWA. You would use a dosimeter worn all day for that. But a SEL is designed to protect workers from acute peak exposures that happen in brief bursts.
So you wouldn't sample for 8 hours?
No, you sample for exactly 15 minutes. You attach a personal sampling pump to the employee expected to have the highest exposure, and you run it for a 15-minute window during the specific task that releases the most ethylene oxide.
What happens if you run it for the whole shift anyway?
If you sample for 8 hours, the brief spike in exposure gets mathematically diluted by the hours of zero exposure, giving you a completely false sense of security.
That dilution concept is tricky, but crucial. Let's fire off a few more chemical and environmental hazard specifics while we're here. When assessing airborne silica dust, which we know causes silicosis, what specific particle size is the most dangerous to human health?
The exam will likely target the 1 micron size.
Why 1 micron?
Well, particulates larger than 10 microns are generally caught by the body's upper respiratory defenses, the mucus and cilia in your nose and throat. But at 1 micron, the particle is small enough to bypass those defenses, travel deep into the lower lungs, and permanently lodge in the alveolar region where gas exchange occurs.
And that causes the irreversible scarring.
Exactly.
And what about radiation physics? The sources gave us scenarios comparing alpha, beta, and gamma radiation shielding. Let's stick to alpha and beta for now.
Alpha particles are heavy. They are essentially helium nuclei. Because they possess such significant mass and a double positive charge, they interact heavily with matter and lose their energy very quickly.
So they don't go very far.
Right. Therefore, an external source of alpha radiation can be stopped by something as thin as a sheet of paper, or even just a dead layer of skin on your body.
But beta particles are different.
Beta particles are high-speed electrons. They are much lighter and penetrate further. To shield against beta radiation, you need denser materials like glass, aluminum, or lead.
Okay, so we've talked about mitigating airborne hazards and chemical burns. But what happens when the hazard isn't a substance, but the kinetic energy of the machine itself?
Hazardous energy.
Yeah, topic 6. That invisible stored power is exactly why OSHA had to step in with 29 CFR 1910.147. Let's dive into hazardous energy control, specifically lockout, tagout, or LOTO.
LOTO is arguably one of the most vital administrative controls in existence. Its entire purpose is to protect workers from the unexpected startup of machinery or the release of stored energy during maintenance.
And it has specific requirements.
Yes, it requires the employer to develop a written energy control program, create equipment-specific procedures, and provide standardized locks and tags.
The psychology of the lock is fascinating to me. It's not just about turning a machine off, is it? It's about transferring the physical control of that machine's life or death power directly into the pocket of the worker servicing it.
That's beautifully put.
Because as long as they hold the key, the machine cannot wake up.
Yet is the exact mechanism of safety at play. And because it is so critical, the terminology matters. The exam will test you on who is actually allowed to perform a LOTO procedure.
It's not just anyone on the floor. It has to be an authorized employee.
Correct. You have affected employees, the people who normally operate the machine, and authorized employees who are specifically trained to lock it out. An affected employee cannot perform LOTO unless they are also cross-trained and designated as authorized.
And these procedures have to be audited. How often must the energy control procedures be inspected?
At least annually. But here is the trap in the practice questions. The periodic inspection must be performed by an authorized employee who is not the one currently utilizing the specific energy control procedure being inspected.
So you can't audit your own work.
Exactly. You need an independent set of eyes to ensure complacency hasn't crept in.
And what about the tags themselves? They can't just be a sticky note that says broken.
No. The standard dictates that tagout devices must explicitly warn against hazardous conditions. They must use universally understood language. Do not start, do not open, do not close, do not energize, do not operate. It leaves absolutely zero room for interpretation.
Let's carry this concept of hazardous energy right into topic 7, general electrical principles. Electricity is the ultimate invisible hazard. The sources bring up a very common office and factory floor issue, which is daisy-chaining power strips.
Oh, you see this everywhere.
You really do. Why is plugging one power strip into another in series considered such a severe safety violation?
It comes down to electrical resistance and heat generation, which violates the Underwriters Laboratories, or UL, listing of the device. A power strip is rated for a specific maximum amperage.
Right.
When you daisy chain them, you are compounding the electrical load drawn through the first strip's cord. The internal wiring isn't thick enough to handle that increased current without generating excessive heat, which degrades the insulation and eventually sparks a fire.
Which leads perfectly to my next question about the electrical panel itself. When a circuit breaker trips because the amperage exceeds its rating, what hazard is it actually preventing?
A lot of people mistakenly believe a standard circuit breaker protects human beings from electrocution.
That's what I thought for a long time.
It does not. A standard breaker protects the physical building from fire. It is designed to interrupt the circuit before the wires inside your walls overheat and ignite the surrounding materials.
So if a standard breaker doesn't protect the human heart from a lethal shock, what does?
For human protection, especially in potentially wet or highly grounded environments, you must use a ground fault circuit interrupter, or GFCI.
How does a GFCI know the difference between a machine running normally and a human getting shocked?
A GFCI monitors the balance of electrical current moving through the circuit. It measures the current going out on the hot wire and the current returning on the neutral wire. Under normal conditions, those two numbers should be identical.
Okay, so what if they aren't?
If even a tiny fraction of a milliampere goes missing, meaning it has found a ground path through a human body or water, the GFCI detects that imbalance and severs the circuit in a fraction of a second, long before the current can induce ventricular fibrillation in the heart.
That is a brilliant piece of engineering. We are essentially measuring the math of the current to save a life. Okay, this brings us to a massive part of the review, topic 8, key safety fundamentals. This covers everything from trenching to confined spaces, and it is just rich with practical mathematical applications.
It's the core of field safety.
Let's start down in the dirt with part A, trenching and excavations. Why is dirt so dangerous?
Trenching is incredibly dangerous because the hazard is deceptive. Dirt doesn't look threatening until it moves. A single cubic yard of soil can weigh roughly 3,000 pounds.
Wow.
That's the weight of a compact car. If a trench collapses, the worker isn't just buried. The sheer mechanical pressure of the soil crushes their chest cavities so they cannot inhale, leading to asphyxiation in minutes.
Which is why OSHA strictly regulates sloping, benching, and shoring based on soil types, right? Type A, B, and C.
Exactly. You have to assume the earth wants to close that hole and you have to engineer a way to hold it back.
But what about when we go in the opposite direction? Part B, working at heights. The physics here are equally unforgiving.
When reviewing fall protection, candidates must understand full clearance calculations. It's not enough to just wear a harness and a lanyard.
You have to do the math.
You have to calculate the length of the lanyard, plus the deceleration distance of the shock absorber tearing open, plus the height of the worker, plus a safety factor.
So if you get that wrong...
If you tie off with a 6-foot lanyard, but you're only working 10 feet above the lower level, you will hit the ground before the fall arrest system fully deploys.
You also have to consider the pendulum effect, right?
Yeah.
If your anchor point isn't directly overhead and you fall, you swing like a pendulum, which can cause you to slam laterally into a structural beam with fatal force.
Precisely. The geometry of the anchor point is just as critical as the strength of the harness.
Moving on to part C, slips, trips, and falls. This seems so basic, but it's a huge source of injuries.
It is. It largely comes down to the coefficient of friction in housekeeping. But let's shift to the factory floor. Part D, machine guarding.
Oh, yes. The practice scenarios ask a fascinating question about human participation here. Which type of machine guarding technique requires the least amount of participation from the employee? A pull-out device, a physical restraint, a two-hand control, or a physical guard?
We have to evaluate the human burden of each control. Pull-out devices and physical restraints require massive participation.
Because they have to wear them.
Right. The employee has to consciously strap themselves in, adjust the cables to their specific arm length, and remember to hook up every single time they approach the machine.
What about two-hand controls?
Two-hand controls, where you must press two buttons simultaneously to actuate the press, require active participation and are notoriously easy to defeat by taping one button down.
I've seen that happen. So by process of elimination, the physical guard is the answer.
Yes. A polycarbonate shield or a metal grate bolted over the point of operation requires zero participation from the operator. It protects them passively, whether they are focused, tired, or distracted. It is a true, robust engineering control.
Now, let's talk about moving materials around that factory floor. Part E, powered industrial trucks, specifically forklifts. I've seen the videos of forklift tip-overs. It's all about the center of gravity, isn't it?
It is entirely about the stability triangle. A forklift doesn't have a rectangular base of support like a car. It pivots on the rear axle, creating a three-point triangle.
Okay, so what happens when it picks something up?
When a forklift picks up a heavy load, the combined center of gravity shifts forward. If the operator turns too sharply, elevates the load while moving, or drives on an incline improperly, that center of gravity shifts outside the boundaries of the stability triangle, and the vehicle tips over laterally.
And the instinct of the driver is always to jump out, which is usually when they get crushed by the overhead guard.
Exactly. The training is to stay strapped in, brace yourself, and lean away from the fall. That behavioral training is critical because it fights human instinct.
Let's scale up the lifting. Part F, hoisting and rigging. I want to spend real time on this because the math questions terrify people, but they are actually beautifully logical once you see the mechanics. Let's look at the tower crane physics problem from the source text.
This is a classic moment calculation dealing with rotational force or torque. Let's set the scene. You have a tower crane. The main boom extends 100 feet forward from the cab. There's a short boom extending 20 feet backward.
Got it.
Sitting on that short boom is a massive 40-ton counterweight. The operator needs to pick up a 10,000-pound object and place it exactly 40 feet out on the main boom. The question is, where must the operator position that 40-ton counterweight on the short boom to perfectly balance the crane?
Okay, let's break the physics down step by step for everyone listening. The formula for a moment is force multiplied by distance from the fulcrum. The fulcrum is the center of the tower. For the crane to not snap in half, the moment on the front boom must exactly equal the moment on the back boom.
Correct. We have a teeter-totter, and we need to balance the math on both sides. Let's calculate the load side first.
The force is the weight of the object, which is 10,000 pounds. The distance is 40 feet out on the boom. So 10,000 multiplied by 40 gives us 400,000 foot-pounds of rotational force, or moment.
Excellent. Now we know the counterweight side must also generate exactly 400,000 foot-pounds to keep the crane level. What is our force on the backside?
The problem says it's a 40-ton counterweight. But here is where people make a fatal math error on the exam. They mix their units.
They absolutely do.
We used pounds for the load, so we have to use pounds for the counterweight. 40 tons multiplied by 2,000 pounds per ton equals 80,000 pounds of force.
Perfect. So we have 80,000 pounds of force multiplied by an unknown distance equals 400,000.
We just divide. 400,000 divided by 80,000. The zeros cancel out, leaving us with 40 divided by 8, which is 5.
The answer is 5 feet. The 40-ton counterweight must be mechanically positioned exactly 5 feet away from the center mast on the short boom to balance the 10,000-pound load sitting 40 feet out.
It's so simple when you break it down.
When candidates realize that these terrifying crane problems are just basic algebra force times distance, the anxiety disappears.
It's just a giant seesaw. And rigging the load to the crane introduces its own physics, too. There's a question about using a 20-foot sling. Which configuration allows the greatest amount of weight to be picked up?
The vertical basket hitch. When you cradle the load and bring both ends of the sling up to the hook, you are effectively dividing the tension across 2 legs of the sling instead of 1.
So you double it.
Assuming those legs are perfectly vertical, you have doubled the lifting capacity of the sling. However, if the angle of those legs spreads out, the tension multiplies drastically, which is why sling angle calculations are so critical to rigging safety.
The closer the angle gets to horizontal, the closer the sling gets to snapping, even with a really light load. It's all vectors. Okay, let's jump over Part G, scaffolding, and move from lifting heavy things to preventing catastrophic chemical disasters. Parts H1 and H2, OSHA Process Safety Management, or PSM, and CCPS, Risk-Based Process Safety, RBPS.
PSM is a direct regulatory response to historical tragedies, like the catastrophic gas leak in Bhopal, India, or the explosions at Texas City. The 14 elements of OSHA PSM are designed to tightly control highly hazardous chemicals.
What are some of those elements?
It mandates deep mechanical integrity programs, process hazard analyses, and strict contractor management, among others.
And the CCPS risk-based process safety model expands on that with 20 elements, focusing heavily on building a robust safety culture and operational discipline. It acknowledges that having the binders on the shelf just isn't enough, right? The organization has to actually live the procedures.
Absolutely.
Which ties right into part one, confined spaces, because a confined space is the ultimate unforgiving environment.
It really is. A confined space is large enough to enter, has limited means of entry or exit, and is not designed for continuous human occupancy. The primary hazards are atmospheric. You have to understand the stratification of gases.
Right, because gases don't just mix evenly in a tank.
Exactly. If you are entering a sewer or a default, you have to test the atmosphere at the top, the middle, and the bottom. Methane is lighter than air, so it will pool at the top, creating an explosive hazard near the entrance.
And what about heavier gases?
Hydrogen sulfide, which is highly toxic and smells like rotten eggs, is heavier than air. It will sink to the bottom, right where the worker is bending down to fix a valve. If you only test the middle of the space, you miss the explosive ceiling and the toxic floor.
That is terrifying, but totally logical. Let's do a rapid-fire review of the last few fundamentals before we get to incident investigation. Part J, fleet and driver safety, the physics of driving a massive commercial vehicle.
It boils down to perception, reaction time, and braking distance. A commercial truck traveling at highway speeds covers a massive amount of ground in the second and a half it takes for a driver's brain to process a hazard and physically step on the brake.
You can't just stop on a dime.
No. Fleet safety programs have to focus on defensive driving, maintaining following distance, and managing fatigue, because the kinetic energy of a fully loaded tractor-trailer cannot be instantly negated by the brakes.
What about Part K, personal protective equipment specifics? We covered PPE generally, but there are specific material requirements on the exam. For welders, what material is best suited for their protective clothing?
Welders should exclusively wear heavy natural fibers like cotton or wool or specialized leather.
Because of the melting point.
Precisely. If a piece of hot slag hits heavy wool, the wool might smolder or char, but it provides a thermal barrier. If slag hits a synthetic polymer like polyester or nylon, the plastic immediately melts and fuses directly to the worker's skin.
That sounds awful.
It turns a minor burn into a horrific deep tissue injury requiring skin grafts. The material science really matters.
And for eye protection, who sets the standard?
The American National Standards Institute, or ANSI. If safety glasses do not have Z87.1 stamped on the frame or the lens, they are not rated for industrial impact, no matter how sturdy they look.
Last fundamental topic, Part L, compressed gases and pressure vessels.
You must respect the stored kinetic energy here. A standard oxygen cylinder holds gas at over 2,000 pounds per square inch.
That's a massive amount of pressure.
If that cylinder falls over and the valve snaps off, the rapid expansion of gas governed by Boyle's law turns that heavy steel cylinder into an unguided missile capable of punching through cinder block walls. This is why cylinders must be chained upright at all times and stored with their protective caps on.
So we have built this massive fortress of controls. We have engineered the hazards out. We've trained the operators. We've done the math. But we are dealing with entropy and human error. Eventually, something breaks. Someone gets hurt.
It is an unfortunate reality.
That brings us to Topic 9, Incident Investigation, and Topic 10, Management of Change. When an incident occurs, how do we find out what actually happened rather than just blaming the guy who pushed the wrong button?
Blaming the frontline worker is the hallmark of a failed safety culture. Human error is a symptom of a systemic flaw, not the root cause. To find the root cause, the sources highlight tools like the Fishbone diagram, also known as an Ishikawa diagram.
I am a very visual learner, so the Fishbone makes a lot of sense to me. Walk me through the mechanics of building one in a post-incident review meeting.
You start with a whiteboard. You draw a horizontal line right through the middle. At the head of this fish on the far right, you write down the specific discrete incident. Let's use a real-world example. Worker amputated finger in stamping press.
Okay, that's the effect. Now we need the causes.
Right. You draw diagonal branch lines extending off that central spine. These represent major categories of contributing factors. In manufacturing, we often use the 6 M's: man, machine, material, method, measurement, and Mother Nature, meaning the environment.
So we start interrogating each category.
Yes. Under machine, you might note that the physical interlock guard was broken, but you don't stop there. You use the 5 whys technique to drill down into a sub-branch.
Okay, how does that work?
Why was the interlock broken? Because the proximity sensor failed. Why did the sensor fail? Because it was coated in heavy machine oil. Why was it coated in oil? Because the maintenance schedule for cleaning the sensors was extended from weekly to monthly to save money.
Wow. So we just went from the worker put his hand in the machine to the procurement department's budget cut caused a sensor failure.
Exactly. The Fishbone diagram forces the investigation team to look past the bleeding finger and examine the environment, the management systems, and the operating procedures that created the conditions for the injury.
And once you uncover that massive systemic flaw, you have to fix it, which is a dangerous process in itself. That leads us right into topic 10, management of change, or MOC.
MOC is the formal process of evaluating and controlling risk when you alter a system. It is a core pillar of process safety management. The reality is, organizations are complex systems. When you change one variable, you create a ripple effect of unintended consequences.
Give me an example of how a well-intentioned change can cause a disaster if MOC isn't applied.
Let's say an engineering team decides to replace a carbon steel pipe with a stainless steel pipe because stainless is more corrosion resistant. Sounds like a safety upgrade, right?
Sure. Sounds like a good idea.
But they bypass the formal MOC process. They don't consult the metallurgists or the safety team. It turns out the specific chemical flowing through that pipe at that specific temperature reacts with the nickel in the stainless steel, causing severe embrittlement and catastrophic rupture.
Because they didn't review the change cross-functionally, their upgrade created a bomb.
Exactly. MOC requires that before any physical, chemical, or procedural change is made, a multidisciplinary team must review it, update the piping and instrumentation diagrams, train the operators on the new hazard profile, and update the hazard analysis. It stops the butterfly effect of unanalyzed modifications.
And to track whether these systems are actually working over time, we use topic 11, leading and lagging indicators. This is a crucial concept for the exam and for professional practice.
Lagging indicators are reactive. They measure failures that have already occurred, like total recordable incident rate or the number of workers' compensation claims. They tell you how badly you failed last year.
It's like looking in the rearview mirror.
Precisely. Leading indicators, on the other hand, are proactive. They are predictive metrics that measure the health of the safety system before an accident happens.
Like what?
This includes the number of near-miss reports submitted, the percentage of preventative maintenance tasks completed on time, or the number of safety audits conducted. If your leading indicators start dropping, if people stop reporting near misses and maintenance gets delayed, your lagging indicators will inevitably spike a few months later.
The leading indicators are the canary in the coal mine. And speaking of the future, the final topic in Domain 2, topic 12, touches on emerging technologies. We are seeing safety fundamentally transformed by AI, drones, and wearables.
The integration of technology is shifting the hierarchy of controls. We are using drones to inspect confined spaces and high-elevation flare stacks, physically removing the human from the hazard. That is an elimination control powered by technology.
Yeah, it's incredible.
We have biometric wearables that monitor a worker's core body temperature and heart rate, predicting heat stroke before the worker even feels dizzy.
The data streams are becoming just as important as the physical guards. Okay, I want to take a breath here and just zoom out for a second. We have unpacked a mountain of discrete, highly technical topics today. ANSI standards, LOTO, risk matrices, crane physics, leading indicators. But the exam and real life requires us to see how all these pieces snap together into one cohesive safety management system.
I'm really glad you brought this up. The exam doesn't just test definitions, It tests synthesis. Let's trace the complete life cycle of a hazard through everything we've just discussed to see the ecosystem at work.
Let's do it.
It begins with an organization committing to ANSI Z10, or ISO 45001. Management provides the budget, and employees provide the operational reality. Together, they form a team to assess a new manufacturing process. They sit down and conduct the HAZOP. They look at the temperature and flow parameters and ask, what if this overheats?
So they identify the hazard, then they pull out the risk matrix. They plot the probability of the machine overheating against the catastrophic severity of a fire, and it lands in the red zone, high risk.
Now they must act. They consult the hierarchy of controls. They can't eliminate the heat. The process requires it. So they install an engineering control, a thermal interlock that automatically shuts the machine down if it exceeds 200 degrees.
But the machine still needs maintenance, so they implement an administrative control. A strict lockout-tagout procedure so the maintenance tech doesn't get crushed while cleaning it. And they mandate PPE thermal gloves, just in case.
6 months later, production wants to swap the lubricating oil to a cheaper brand. This triggers the management of change process. The team analyzes the new oil, realizes it has a lower flash point, and updates the thermal interlock to shut down at 180 degrees instead of 200.
But let's say a year later, a tech bypasses the LOTO procedure because they are rushing and they suffer a severe burn.
The organization initiates an incident investigation. They use a fishbone diagram and discovered that the root cause wasn't just the worker rushing. It was a production quota that heavily penalized downtime, motivating the shortcut. That lagging indicator, the burn injury forces management to review their leading indicators, realizing they hadn't done safety culture training in a year.
And all of those findings feed directly back into the evaluation and planning stages of the ANSI Z10 continuous improvement cycle. They adjust the production quotas, retrain the staff, and the system grows stronger. It really is one living, breathing ecosystem. You pull one thread and the entire web vibrates.
That is the big picture. That is what separates someone who just memorized flashcards from a true safety professional.
And that brings us to the end of our Domain 2 session. We have covered an incredible amount of material today, synthesizing the very best of our authoritative sources into actionable knowledge. I want to enthusiastically congratulate you, the listener, for finishing the entire ASP 11 Domain 2 playlist. Getting through this dense material is a huge accomplishment, and you have put yourself in an incredibly strong position.
I echo that completely. And I want to emphasize that this isn't just an academic exercise to pass the ASP or CSP exam. Yes, passing the exam is your immediate objective, but the physics, the psychology, and the systems we review today form the absolute bedrock of your daily practice.
That is the real deal.
Understanding how a risk matrix translates engineering data to leadership, or how a fishbone diagram prevents a repeat tragedy, that is what allows you to build environments where real people survive hazards and go home to their families every single day.
That is the real mission. Thank you so much for your support and for choosing to learn with QHSE Talks. If this review helped connect the dots for you, please take a second to like the video, subscribe to the channel, and share this playlist with other safety professionals, your colleagues, and anyone else out there grinding as an ASP or CSP candidate. We are trying to build a global community of highly informed, highly effective safety leaders, and your support makes that possible.
As we wrap up this session, I want to leave you with a final thought to mull over. Throughout this review, we've talked extensively about calculating risk based on probability and severity matrices. We talk about acceptable risk thresholds, standard deviations, and 1 in a million chances. We take comfort in the math that says a catastrophic failure is highly improbable.
Right, we rely on the numbers.
But remember this. To the worker who actually gets caught in the machine, to the rigger who is standing under the crane when the sling snaps, the probability of that event wasn't a fraction. For them, the probability was 100%. It happened. The statistics offer no comfort to the victim. How does acknowledging that stark reality change the way you look at your next safety audit? When you are deciding whether an administrative control is good enough, ask yourself if you would bet a 100% consequence on it.
That is a powerful grounding perspective to carry with you onto the factory floor and into the exam room. Keep analyzing the systems, keep improving the culture, and keep leading with safety. We will see you on the next session of QHSE Talks.
Best of luck on your exams and stay safe out there.